Hi students, please subscribe my channel Nana. Thank you students. In today's session I am going to discuss about the crystal field theory Nana, splitting of d orbitals in tetrahedral complex. Okay na, this is the topic from coordination compounds 12th class Nana. Now see here tetrahedral complex. If I take tetrahedral complex Nana, this is central metal atom. Total 4 ligands are occupied around the central metal atom. 4 ligands will be there. Now once you observe students, these 4 ligands are present along the Cartesian axis. No, they are not present along the Cartesian axis. Cartesian axis means x axis, y axis, z axis. Okay. Now see here, these 4 ligands are not present along the Cartesian axis. They are present in between the Cartesian axis. Yes or not? This is x axis, this is y axis, this is z axis. That means in between the Cartesian axis only these ligands are occupied. That means what we can say, these ligands are calling as non-axial. Are you understanding? Axial means what? Ligands, if suppose all ligands are present along the Cartesian axis, then we'll call it as axial orbitals. But here total 4 ligands are present in between the Cartesian axis. So that's why these 4 ligands are calling as non-axial. Now you have to see in metal atom, total 5 d orbitals will be there. In the metal atom, in d subshell, total 5 d orbitals will be there. Yes or not? Once I will show you Nana. See here, degenerate orbitals. Degenerate, because this is a d subshell. Total 5 d orbitals named as dxy, dyz, dzx, dx square minus y square, dz square. These 5 d orbitals are calling as degenerate orbitals because they have the same energy, students. Are you understanding? Because they have same energy, and their shapes also I given Nana here. dxy, dyz, dzx all are having the same shapes. That means the lobes are present in between the Cartesian axis. That's why these three shapes dxy, dyz, dzx, these three orbitals are calling as T2G orbitals in octahedral complex. But in the case of tetrahedral complex, students, we are named as T2 orbitals. We are not taking G. In octahedral we are taking T2G, but in the tetrahedral complex we are taking only T2. Are you clear? These three are non-axial because the lobes are present in between the Cartesian axis. But in the case of last two, dx square minus y square and dz square, in these two orbitals the lobes are present along the Cartesian axis. Are you understanding? So along the Cartesian axis there, that's why these two orbitals are calling as axial orbitals. Okay na? So in octahedral complex these two orbitals are named as Eg, but in tetrahedral complex we are named as E orbitals. Are you understanding? Okay, the G1, T2G, Eg, these two are octahedral complex. T2E are tetrahedral complex. Are you understanding, Nana? T2E. These two are octahedral complex. T2E. These two are tetrahedral complex. Are you clear this one? Tetrahedral complex, students. Okay. Are you clear? So what is non-axial, axial? So these are non-axial orbitals. These two are axial orbitals. Understood, Amma? Now see, students, here what we are discussing, tetrahedral complex we are discussing. See, tetrahedral complex. Here 4 ligands are non-axial or non-axial. That means 4 ligands are not present along the Cartesian axis. They are present in between the Cartesian axis. That's why we are calling as non-axial. Okay. Now, in the metal atom, total 5 d orbitals are there. T2E, already I showed you. T2E. T2 is non-axial, E is axial. So 4 ligands non-axial. In these two, which is non-axial? T2 orbitals are non-axial. That means ligands, these 6 ligands non-axial and T2 non-axial. Are you clear? Non-axial. That means T2 orbitals, 4 ligands. Are you understanding? T2 orbitals, this T2 orbitals, 4 ligands, both are in the same plane because non-axial, non-axial. Are you understanding? Both are in the same plane. That means here whenever four ligands come closer to the central metal atom, what happened? Between them repulsions are taking place, students. That means in the metal atom already in d subshell electrons will be there. In four ligands also electrons will be there. Between the electrons repulsions are taking place. And next these four ligands and next T2 orbitals, non-axial orbitals, both are in the same plane now. Both are non-axial. That means both are in the same plane. Are you understanding? Now both are in the same plane, but E orbitals were there along the Cartesian axis. Okay, now along the Cartesian axis. That means these four ligands strongly repelling the T2 orbitals. These three orbitals it is repelling strongly. Okay, now it is repelling strongly because both are in the same plane, non-axial. Are you clear? Both are in the same plane. So that's why they repel they repel strongly, Nana, T2 orbitals. So what happened, Nana? T2 orbitals energy is increased. That means T2 orbitals are goes to up. Their energy is raised. And coming to the E orbitals, there are here also repulsions will be there. But when compared to T2, these E orbitals repulsions are less, Nana, because they are not in the same path of ligands. Because these are axial, ligands are non-axial. That means in between them repulsions are less when compared to T2. Because T2 orbitals, four ligands, both are in the same plane, non-axial. That's the same plane now. Same plane means repulsions are more. Are you clear? Repulsions between the ligands and the T2 orbitals, repulsions are more. Are you clear? Repulsions more. So whenever repulsions more, what happened? T2 orbitals energy is raised. That means T2 orbitals, three orbitals are goes to up, and E orbitals, axial orbitals energy is decreased. They comes down. Are you clear? They comes down. See here, total 5 d orbitals, degenerate orbitals, they have the same energy. Total 5 d orbitals are having the same energy. Are you clear? Same energy. Whenever ligands approaches to the central metal atom, what happened? They loses their degeneracy. That means their total 5 d orbitals are split into two sets, Nana. One is lower energy orbital, another one is higher energy orbitals because of repulsions of ligands. Now I will show you, Nana. See here, total 5 d orbitals, degenerate orbitals I am taking 1, 2, 3, 4, 5. These are degenerate orbitals. Degenerate orbitals. That means they have the same energy. Correct or not? What are the names? dxy, dyz, dzx, dx square minus y square, dz square. This total 5 d orbitals, so degenerate orbitals. That means they have the same energy. Are you understanding? They have same energy, Nana. Same energy. Now these orbitals are split into, see here, split into, first they loses their degeneracy. That means whenever four ligands come closer to the central metal atom, these 5 d orbitals loses their degeneracy. That means their energy is changed, Nana. See here, total 5 d orbitals loses their degeneracy. 1, 2, 3, 4, 5. Okay, so total these 5 orbitals also loses their degeneracy. That's why we are calling as non-degenerate orbitals. What we are calling? Non-degenerate orbitals. Are you understanding? That means they loses their energy, students. Are you clear? So what are the names? dxy, dyz, dzx, dx square minus y square, dz square. Now these total 5 d orbitals are split into, Nana, two sets, Nana. First one is, see here. So here ligands, so T2 orbitals both are the same plane. So that means T2 orbitals energy is rise, they will go to the up. That means this T2, three orbitals, dxy, dyz, dzx, these three orbitals will come to the up, Nana. So here I am taking the three orbitals. 1, 2, 3. Next, E orbitals are repulsions less, so that's why their energy is decreased. So that's why what will happen? They comes down. Dx square minus y square, dz square. Total 2 d orbitals are comes down. So what are the names, students? This is T2. This is E. Correct? What are the names? dxy, dyz, dzx. These two orbitals names what? Dx square minus y square, dz square. So this is the crystal field splitting energy. This energy gap is there now between the two sets of d orbitals. This energy gap is calling as delta t. That means crystal field stabilization energy. Crystal field stabilization energy. Are you clear? Stabilization energy. Crystal field stabilization energy is nothing but what, Nana? The energy difference between the two sets of d orbitals. This is the energy gap between the two sets of d orbitals. Energy gap between the two sets of d orbitals is called crystal field stabilization energy. Now I have to find energy of these two orbitals. First I am going to calculate T2 orbitals energy. Now see students, T2 orbitals energy. Here total 5 degenerate orbitals, na total 5 there. So write here first in the denominator that number, total 5 orbitals. Out of 5, how many orbitals energy is decreased? 2 orbitals energy is decreased. Their energy is more, this energy is less. Are you clear? So how many orbitals energy is decreased? 2 orbitals. So that numerator you have to take 2 orbitals, and their energy is, this 3 orbitals energy is raised now. So that's why we have to take the positive sign into delta t. Delta t you have to multiply. What is delta crystal field stabilization energy? T indicates the tetrahedral complex. Crystal field stabilization energy in the tetrahedral complex. Okay. So this is the T2 orbitals energy, Nana. 2 by 5 into delta t. So what we can write? 2 by 5 is nothing but plus 0.4 delta t. Clear? Plus 0.4 delta t. Now coming to here, E orbitals energy. E orbitals energy, Nana. Total out of total how many orbitals? 5. Out of 5, Nana, how many orbitals energy is increased? 1, 2, 3. When we are calculating this energy, these orbitals energy you have to take. These orbitals, how many orbitals energy is increased? That number you have to take in the numerator. Denominator same only, 5, 5. So here what I am taking 2, means when we are calculating this energy, this orbitals number you have to take in the numerator. When we are calculating this orbitals energy in the numerator, these orbitals number you have to take. Next, these orbitals energy is more na, positive. These orbitals energy less na, decrease na, so that's a minus. So into delta t. Then what you will get, students? Answer minus 0.6 into delta t. Correct? Minus 3 by 5 is nothing but minus 0.6 into delta t. Clear, students? Clear, Amma? So here 4 ligands, T2 orbitals both are non-axial. So that's why between them strong repulsions are taking place. That's why T2 orbitals energy is raised. That's why they are going to up. These E orbitals axial, these ligands non-axial. So that's why between them also repulsions will be there. That's why what happened? Their energy is decreased. That's why they comes down. Are you clear? Total 5 degenerate orbitals split into 2 sets, Nana. These are degenerate, these are non-degenerate. They loses their degeneracy. That means their energy is changed, not equal. Okay, now here same energy, they don't have the same energy here. Here split into 2 sets, they have the more energy, they have the less energy. That's a positive, here negative. Are you clear? Okay, now this is the crystal field splitting in the tetrahedral complex, students. Okay, Nama, I hope you like this video, students. If you like this video, please like, share, comment and subscribe my channel, Nana. Thank you, students.